Batteries, fuel cells, supercapacitors. All are electrochemical storage devices. But what's the difference? Why are there so many different sorts, and what are they good for? Batteries are possibly the most interesting electrochemical storage device at the moment because of their potential to be used by ordinary households, particularly in conjunction with renewable energy sources, to reduce the amount of electricity they use from the grid. But there are a lot of different ideas out there, ranging from it's vital to we're not ready, from it's cheap to it's expensive. The economics aren't simple. The capital cost is currently high, but the situation is constantly changing. People are looking for batteries to do everything, from peak shaving or peak shifting to frequency fixing or avoiding price spikes. It's a fast-moving space, so let's first cover the basics. Electrochemical storage devices all have similar operating principles, but they all work slightly differently. Broadly speaking, you can divide electrochemical storage devices into three types: batteries, supercapacitors, and fuel cells. Now I'll talk about batteries and supercapacitors. Fuel cells I'll leave for another time. Let's start with batteries. How does a battery actually work? For a battery to work, you need two materials that have an electrochemical potential difference and a medium for charged particles to flow through. Once in the battery, the materials are called electrodes. The positive one is the cathode, and it has a lower electrochemical potential than the negative electrode, or anode. When you connect the electrodes with a wire, electrons travel through the wire, moving from the anode to the cathode, and the potential difference is balanced out by the negative anions flowing in the opposite direction across a membrane or salt bridge. When you recharge a battery, you reverse the flow of electrons by adding in a power supply, and the ions flow back, uphill as it were, to revert back to the starting materials. There are multiple different combinations of metals, electrolytes, and materials that can be used for battery making, and they all have different electrochemical potentials. The reaction kinetics and stabilities can be different too, so there's a lot of work that goes into selecting the right combination of electrodes and electrolyte to make a battery. Supply, disposal, and potential to recycle the electrodes is also an emerging issue as we use and discard more and more batteries. Modelling in the literature shows that the production of rare earth materials, which are required for the newer battery technologies, may be insufficient to meet that demand. This makes older technologies like lead-acid batteries look better than they otherwise might because they're highly recyclable. As well as using different materials, different batteries have different discharge characteristics. The discharge characteristics of some non-rechargeable batteries are shown on this chart. On the y-axis you have voltage, and on the x-axis there is time. Ideally, you want a very long operating life at the same voltage. So it's only at the very end that the voltage isn't high enough to power your device. Lead-acid batteries are an interesting case here. Lead-acid batteries are found in cars, and car battery performance used to tail off as the battery was nearing the end of its life. So people would use this as an indication that their car was likely to need a new battery soon. The new control systems in cars give you a much flatter response, which helps it last longer, but it also means that unfortunately now your car battery just stops working with little to no warning. Probably the battery that you hear most about is the lithium-ion battery. Why is it so familiar? They're familiar because they end up in lots of devices. But why are lithium-ion batteries chosen over other sorts? Well, that's easy. Lithium-ion batteries have good power density, good energy density, good capacity. They don't self-discharge like the old nickel-cadmium batteries did, and they don't have cadmium, which is a toxic metal. Another interesting but relatively new battery is the flow battery. Flow batteries are practically infinitely rechargeable. A flow battery, rather than storing the two materials with a potential difference next to each other, stores them apart, literally, in separate containers. Then, when you want to extract energy from the battery, you typically pump them past each other with a membrane in between. Ion exchange occurs, and they generate electricity. When you want to recharge the battery, you bring the fluids into the cell again and flow electricity through them to reverse the chemical reactions. and you end up with the same two solutions that you started with. This means that the battery can be cycled potentially indefinitely. These aren't the sorts of things you'd expect to be powering your phone anytime soon though. They are for kilowatt or greater scale installations and can be the size of a shipping container. Now let's move on to supercapacitors. Supercapacitors have a similar design to batteries in that there are electrodes and an electrolyte. Unlike batteries, however, there are no chemical reactions occurring in supercapacitors. Supercapacitors basically work by separating charges out and storing them in a material which has a huge surface area. The supercapacitor keeps the charges apart until you connect it to a circuit. Once it's connected, the charges quickly flow around to restore the balance. This means that supercapacitors discharge very quickly, but they can't store much energy. So why are there so many different electrochemical storage devices? Well, we need a variety of devices because they each have their own characteristics which suit the demands of different systems. For example, if you compare batteries and supercapacitors, you can see that batteries have a higher energy density, longer discharge time, and weigh much more. But supercapacitors have an enormous power density and can be cycled much more frequently than batteries. This means that if you want energy storage for later, you might use a battery. But if you want to control the power quality and stop brownouts, then you might use a supercapacitor. It's just a matter of finding the storage device that fits your system's needs. Batteries have come a long way in the last 15 to 20 years, but opinion is still divided on their role in the future of major energy reform, with the headlines varying from energy storage is vital, but industry isn't ready, to vanadium flow batteries, the energy storage breakthrough we've needed. And despite the hype, batteries aren't the cheapest way to store energy on the grid. So we'll just have to wait and see if batteries live up to their potential.